During this session I'm going to be talking about the length contraction which takes place due to the ideas of special relativity. So, objects moving relative to an outside observer appear contracted in the direction of their motion as measured by the observer. So what we're saying here is everything looks normal in your own reference, but if you measure Jackie's spaceship, you'll find it is shortened in the direction of her motion. So let's explain why this observation comes about. First of all, we're going to define proper length. So proper length is the length of an object or the distance between 2 points whose positions are measured at the same time as measured by an observer who is at rest with respect to it. So this proper length is similar to proper time. It's all about the observer being in the same frame of reference. Now, why does this length contraction take place? Well, if you and I will agree on our relative speed, okay, I see your clock running slower. So that means that if I look at the distance travelled, it's going to be velocity times change in time. But if we agree on the velocity and I see your clock running smaller, that means that I will measure as you being shorter in the direction of the travel. So that's the key essence here. It's a consequence of recognizing that there is the clock is running slower as perceived. So here we have an object, therefore at rest will have a certain length, but whilst in motion it will appear to contract in the direction of the length, in the direction of the motion, I should say. This is known as Lorentz contraction. Okay, so here's the formula which is given, and let's go through those values. V is the relative velocity between the observer object and the observer. C is the speed of light. L is the measured length of the moving object, and L is the measured length of the object at rest. Okay, so that'd be the proper length. And we're going to use these values in this formula to work out unknowns. So if we're calculating length contraction, we recognize that the proper length divided by Lorentz's function gives us the length which we will see, and therefore this is key to making any calculations. And we've got to remember that because the Lorentz factor is always going to be greater than 1, that means that the length which is observed is always going to be less than or equal to the that of the original length, so therefore it's going to be contracting. Big note here, and this is one thing that people often miss: contraction takes place only in the direction of motion. So if an object is moving horizontally, there'd be no contraction vertically. Okay, so there's one feature which was shown in the earlier diagram. I just want to repeat that factor. We see that if the ball is moving, we see its height doesn't change in any way, but the length in the direction of the motion does do. So why should this be of real interest to people doing space voyages? Well, let's think it through. The center of our galaxy is maybe 25,000 light years away. Now, does that mean if we travel in that direction at the speed of light, it would take 25,000 years to get there? Well, actually no. From an Earth frame of reference, yes, but the space voyagers, definitely not. For the space voyagers, at the speed of light, 25,000 light years distance would be contracted to no distance at all. Space voyagers would therefore arrive instantaneously. So this is the extreme. If you're traveling at the speed of light, then you would be arriving at every point instantaneously, if we could reach that speed. And there's lots of issues associated with that, don't you worry. So that's why it's of interest. Some questions here. I've got 4 questions. Pause, take a moment, try and answer these questions, and I'll come back to the answers in a moment. Okay, let's see how well you've done. The length you would measure would be 3.1 meters for the first question, 2.5 light years for the second question, 2.63 years for the third question, and 2.63 years for the last question. Hopefully that's given you an idea of the impact of length contraction, and this should help you have a better understanding of the complexities of special relativity. What we're going to look at next is some of the, I guess, interesting situations which come up, including something known as the twin paradox. But that'll be in my next session.